Hello everyone, welcome to the Microeconomic Theory 2 course for the 14th April session. Today we'll start a new topic. Specifically, we'll talk about games of incomplete information today. So, topic to be discussed is games of incomplete information. Okay, so what do I mean by games of incomplete information? So far in all the games that we have studied, both simultaneous move as well as sequential move games, there was no uncertainty about the payoff of both the players and the strategies that each of the players can take, right? So all the players exactly knew the entire game, right? It could be that, so in extensive fug games we had considered cases where some players do not observe which specific information, which specific node they are in, so they have sort of this multi-node information sets. But even in that case, the entire game and the payoff consequences of all possible actions taken by all the players are completely known, right? So if the player could know which node they were sitting in, they would know exactly what payoff will materialize, not just for the player himself but also for all the other players, right? So the payoff matrix, so to speak, or the payoff consequences of all possible strategies of all players were common knowledge across all the players, right? So all the players know all the payoffs of each other, right? So that belongs to this broad umbrella class of games of complete information, right? So the games so far that we have been discussing are games of complete information, and today we will allow the possibility that players may not know the payoff matrix entirely. They may have some uncertainty about the payoff consequences, especially with regard to other players. They are sort of unsure about the payoffs that are accruing to the other player for certain possible strategies. Okay, so that set of that if that information is lacking on the part of some players in a game, then those games are referred to as games of incomplete information. Okay, so for example, take the Cournot model, right? In the Cournot model, the demand function is known and the cost functions are also common knowledge across both players, across both the firms, right? But it could be the case that firm 1 is unsure about the cost structure of the opponent firm, right? It could be a high cost firm, it could be a low cost firm, and firm 1 doesn't know exactly what kind of firm the firm 2 is. Firm 2 obviously knows about its own cost structure, it knows whether it's high cost or low cost, but the first firm doesn't know, and that would be a setup of which will sort of fit into these games of incomplete information, right? And we will talk about such kind of a Cournot model later. But to begin with, to sort of set ideas, let's consider a game of the following kind. So suppose there are two players, player 1 and 2, and they have the following payoff matrix. Okay, so player 1 can take actions or strategies A and B, and player 2 can take actions C and D. Okay, so that's player 2, this is player 1, and the payoffs are 3, 6, 6, 9, 6, 0, and x, 9. Okay, so what is this x? This x is the unknown, the uncertain part, not completely unknown but uncertain part. So x can take two possible values. Okay, so x can take two possible values. It can take 12 or 0, right? So it can be either high or a low payoff. So basically what this means is that player one's payoff from taking action A when player 2 takes action C can be either 12 or 0. Okay, and player 1 obviously would know at the time of choosing the strategy whether the payoff is 12 or 0 for him. Okay, but the uncertainty is more from the point of view of the second player. So the second player doesn't know whether player 1 would get payoff 12 or would get payoff 0 from choosing action A when player 2 chooses action C. Okay, now it is not just enough for the game to specify that it can be one of the two cases, it can be 12 or 0. The game must also specify what are the likelihoods of these two payoffs. What is the chance that actually player 1 would get payoff 12, and what is the chance that player 1 would get 0, right? So it's not just enough to say these are the possible things. We must also specify what does 2 believe about the likelihoods of each of these possible payoffs. So let me specify that x is 12 with probability 2/3 and 0 with probability 1/3. Okay, so this means that player 2 thinks that player 1 will get payoff 12 in that cell with probably 2/3 and will get 0 probably 1/3. Okay, so this is the information setup. It is not complete information, but it's not also complete blank, right? If it's a blank, then we can't do much. We have to specify something for us to actually compute optimal actions. So this is the sort of nature of incompleteness of the information. So now this specific information that x can take two values with these two probabilities, this information is common knowledge, right? So both players 1 and 2 know that x can take these two values with these two probabilities, and obviously when 1 chooses its action, 1 can see whether x is 12 or 0, but 2 doesn't. But 1 knows that 2 thinks that 1 could be 1 could get 12 with probably 2/3 and 0 with probably 1/3, and this is important, right? One knows what 2's knowledge is. Okay, and 2 knows that, right? And ad infinitum, right? So the usual definition of common knowledge. Now we will refer to, so basically what this means is that there are two possible payoff matrices. Okay, so let me write down the two possible payoff matrices. Oops, sorry. So let me write down the two possible payoff matrices. So the first payoff matrix is C, D, A, B. It's the 12, 9, 3, 6, 6, 0, 6, 9, or it is the second payoff matrix. C, D, A, B, the 0, 9, 3, 6, 6, 0, 6, 9. Okay, so it is one of the two payoff matrices, and player 2 is unsure. Okay, we will refer to one type of payoff matrix or one type of payoff accruing to player 1 as if as its type of that player, of player 1. So we'll call this the type 12. Okay, and so this matrix refers to the payoff matrix where player 1 is of type 12, meaning player 1 when chooses A and 2 chooses C, player 1 gets 12, as opposed to the matrix corresponding to type 0 of player 1. Okay, so here the corresponding payoff for player 1 is 0, right? So this uncertainty of payoffs we'll call it as if it's uncertainty of type. So basically, you can say that the first payoff matrix refers to the case where player 1 is quote unquote say the high type, right? High type meaning he gets a very high payoff when playing A, right? And type 0 refers to the case where player 1 is the low type player, meaning that he gets a very low payoff. Okay, so we'll map payoff uncertainty to different types of players, right? We'll say that some type of player gets one kind of payoffs, the other type of players get other kinds of payoffs, which then result into different payoff matrices. Okay, now one way to sort of model this uncertainty about types of players and hence different payoffs accruing to the same player corresponding to different types is that first the nature, the chance, first chance decides whether player 1 is of type 12 or type 0. Okay, there is a chance, suppose the chance is a player, or the world, the nature outside is a player, and the nature doesn't have any strategy. It just tosses up a coin to decide whether player 1 will be type 12 or player 1 will be type 0. Okay, so and the coin toss probabilities are given by the probabilities I mentioned here, right? This 2/3 and 1/3. So we will say that first nature or chance moves and decide whether player 1 is of type 12 or type 0. Chance has no objective function. It just moves based on a coin toss, and it chooses type 12 with probability 2/3, and it chooses type 0 with probability 1/3. And once these types are chosen, player 1 can see which type it is. So player 1 can sort of see whether, okay, so I am the type 12 guy, and so player 1 knows which payoff matrix that he's located in, but player 2 is not aware, right? Player 2 only knows that there is a chance, this player called chance who moves with these probabilities across the two arms, and then the game is played simultaneously between player 1 and player 2. Okay, so if I have to sort of express this game in an extensive form expression, so extensive form expression, then it will look like this, that first chance or nature moves, it chooses with probability 2/3 the type 12 and probability 1/3 the type 0, after which player 1 can see. So player 1 knows the movement of nature. Player 1 plays A or B in both cases, right? Player 1 plays either A or B, after which player 2 plays either C or D, or D, but player 2 has no clue. Not only player 2, so the first point is player 1 and player 2 are in a simultaneous move game, so player 2 don't see the actions of player 1 when player 2 chooses its own action. Moreover, player 2 don't see the move of the nature. So player 2 not only doesn't know what player 1 is choosing, it also doesn't know what was the move of the nature. So player 2's information set is actually across the entire, let me just highlight it, it's the entire 4 nodes where player 2 can move. So player 2 basically has only one choice, either say C or D, correct? Because our definition of a strategy is one action for every information set where a player can move. Here player 2 has only one information set, correct? All the four nodes are in the one information set. So this game doesn't have any proper sub game. The entire game is a sub game. Okay, so the game is actually not extensive. The game is not a sequential move. The game is simultaneous move, right? Player 1 and 2 are moving simultaneously. There's a nature which is moving first, but nature is not really a player in the sense we understand players who have a strategies and payoffs, etc. Nature is just a way of expressing the uncertainty. Okay, so the game is sequential move game with an incompleteness of information built inside it, and we are expressing this incomplete information simultaneous move game using this extensive form expression. I'll show how to show it in matrix format in a normal form expression. Okay, so and you can sort of write down the payoffs here. I'm not writing down again. So this is how you can sort of write down the extensive form. Now let's talk about the normal form. So let me just actually in this space itself, let me write down the normal form expression, so the matrix form. So the first thing we have discussed is that player 2 has only one information set, and hence has only one action to choose when it has a chance to move, correct? So it can either choose C or D. So these are the two possible actions or strategies for player 1. Player 2. Player 1 on the other hand has two information sets at the top and here, right? So chance moves first, and then player 1 observes whether it's the player 1 is of type 12 or type 0, and accordingly it chooses action. So its action can be type dependent, type contingent, correct? So by definition of strategy, so if player 1 is of type 12, meaning that if player 1 is in this matrix, then player 1 can say, okay, I'll choose B. If player 1 is in the type 0 payoff matrix, then player 1 can say, okay, I'll choose A, right? So it can say that if I'm type, it can make its choice of action type contingent. Okay, so that's the idea. So given that player 1 has two nodes, it will have to specify two actions, one for each type. Okay, so that's the strategy, right? So it can say I choose A for the top node and A for the bottom node. Okay. In order to sort of ensure that we understand correctly, I'm following the notation in the book, and I'm writing the type on top of it. So I'll write A12 and A0. A12 meaning the type 12, meaning the top node chooses A, and the bottom node, the type 0 guy, chooses A. Similarly, it can be A12B0, right? So it can be A12B0. It can be B12A0. Meaning the top node, so if one observes he is of type 12, he chooses B. In the bottom node, when he observes that he is of type 0, he chooses A. Okay, or it can be B12 B0. Correct? Now, the question is, what are the payoffs? So suppose so these are the four strategies of A, right? A's strategy is type contingent. For each type, it has an action plan. Here the probabilities will come in handy to compute payoffs. Okay, so suppose player 2 chooses C in his information set, and player 1's strategy is A12 A0, basically to choose always A regardless of type. Okay, now the question is, if A's type is the payoffs for AC. So if I go back to this payoff matrix here, payoff for AC is this in this type 12 matrix, and payoff for AC is 0, 9 in the right payoff matrix. Okay, now the question is, what is the payoff in sort of aggregate payoff when player 1 has this strategy of always choosing A? In one case it will get 12, in another case it will get 0. But we know the probabilities of the two metrics, so basically we can compute the expected payoff, right? So the expected payoff here is with probability 2/3, it gets payoff 12. Player 1 gets payoff 12. With probability 1/3, player 1 gets payoff 0. Okay, so then we can compute the payoff and write it here. So payoff from A12 A0 is with 2/3 you get 12, and with a third you get 0. So this is basically 8 for player 1. What is it for player 2? Player 2 in both cases gets 9 and 9. So 2/3 of 9 plus 1/3 of 9 is 9. So it's 9. Similarly, what happens when player 2 chooses D and player 1 chooses A12 A0? So again you see player 1 gets 3 with probability 2/3 and 3 with probability 1/3. So it gets 3, and similarly player 2 gets 6. What if it's A12 B0, meaning player 1 chooses A here, so player 1 gets 12, and on the right player 1 chooses B and player 2 chooses C, so player 1 gets 6. Okay, so 2/3 of 12 plus 1/3 of 6, if you calculate you will get 10. And what about player 2? Player 2 is 2/3 of 9 and 1/3 of 0. Okay, so that gives you 6. If you do this computation, you will get this payoff for this cell, and 4, 3 in the next one, 5, 8 in the next one, 6, 0 and 6, 9. I ask you to sort of go through this and calculate these expected payoffs to see whether the way I've written is actually correct or not. Okay, once we have computed expected payoff, this now gives you the final normal form expression. So this is the normal form expression of the game. Okay, in the normal form expression we are writing down the full strategies of each player, and we are using the probabilities with which the different types are chosen by nature to compute expected payoffs for each player to write down in the cells. Okay, and this is how it is done. So in the next video I'll talk about how to solve these kinds of games.